Hi, everybody. So this is joint work with Michael and Anil, and this is also a talk that I think is situated very well within the program, follows very well with the talks that we just saw. So the motivation for this work is that scientific workflows are increasingly collaborative. Okay, so they're increasingly large-scale collaborations, and they're increasingly loosely coordinated large-scale collaboration. So you might have various field and experimental scientists collecting data, and this is a continuous process. Maybe it's actually coming from things like satellites in climate science. And then you have data scientists cleaning and analyzing this data and publishing these analyses. You have model builders, computational scientists parameterizing system models using this data, and then other model builders integrating these systems models into integrative systems models, it's kind of bigger models of bigger systems. And these might go on to inform various parts of society. So environmental interventions, both public and private, public policy, public engagement. And so collectively, this whole thing can be understood as a sort of collaboration that's ongoing. And these workflows need to be supported by tools. And to support these kind of workflows, the community, maybe used to be called the open science community or the scientific community, has identified a lot of best practices around scientific data and scientific code. So the ones I want to highlight here fall under the rubric of the FAIR criteria. So this is a set of criteria that's pretty well established at this point. And so let me just tell you about these criteria. So the FAIR stands for, one, findability. So this is just stating that we want data and code to be discoverable by the people and the machines that can make use of this data. Closely related one, I think they're really only different to make the acronym work, is accessibility. So in addition to being discoverable, you have to actually be able to retrieve it. Okay, you have to access that data that you found. Now there's a little bit of subtlety there because sometimes access is controlled in some way, right? So maybe they are truly different criteria. A big one is interoperability, right? If you want to have collaborative workflows, you have to be able to actually interop with the data sources, the tools, the code that other people are using, and there's a lot of diversity in the tools that we use, and so this is a major challenge. And then under R, R stands for reusability, but I'm also going to throw in reproducibility under this rubric as well, although it's often discussed separately from the FAIR criteria. So it should be possible to run, or in the reproducible sense, rerun, and modify and build upon these artifacts. It's not about just using them as is, but about making modifications to them and adapting them to other purposes. Okay, so those are the criteria that are kind of central to this talk, and then I'm going to throw in one more that Patrick actually just highlighted in his talk, which is that you have new data, new models arising constantly, especially in climate science, right? And so we want to be able to not just get snapshots of an analysis at a particular point in time when a publication was put online, but rather to be able to easily and quickly and kind of automatically, ideally, update these when the data or the models change in some manageable way. Okay, so fairness and liveness is what I'm going to be talking about here. There are other things we care about as well, but those are the focus areas for today. The core problem, the central problem kind of animating the work that this talk is about is that scientific software tools sort of have bad defaults. So this usual patchwork of software tools that we use to do scientific work, these are often just kind of adapted from other kinds of professional tools that have been developed. They require actually putting in extra work to follow these best practices. So if you just use them in the sort of the normal way, if you're just a graduate student and you're not thinking about the FAIR criteria and liveness and stuff, you're just thinking about your next publication, you're doing some modeling of fish patterns in the ocean, right? You're not thinking about these things. You're not going to put in that extra work. And so the defaults really matter. And we know that the defaults really matter in general, in design, right? This is something that is well understood. And we have bad defaults. The tools that we use today are not designed to support these kind of collaborative scientific best practices by default, and so often we don't achieve these criteria. And so let me consider a particular tool as a central example here. So the tool that many scientists use is very central to their work is a computational notebook system, something like Jupyter or its various cousins. Okay, so I assume most of you have seen Jupyter before, but if you haven't, it kind of looks like this, right? You have code, and you have figures, and you have various authoring things going on here. And what you do as a scientist is you kind of do your day-to-day work in Jupyter, and let's analyze this from using these criteria. And so I'll argue that in some sense, Jupyter fails in all of these ways in terms of its default usage. So findability and accessibility, by default, when you create a Jupyter notebook, it's just sitting locally on whatever machine the Jupyter server is running on, and you have to put in a lot of extra work in order to make it public and accessible in some way, and it's actually quite tricky to do that. Interoperability, so one Jupyter notebook, even on your own machine, can't really access another Jupyter notebook. The code, the data on another notebook is not easy to access. There are kind of hacky mechanisms to do this, but it requires just re-executing that one notebook in another. Even if all you want is some helper function that was defined in the other notebook, you have to rerun the entire analysis, and then you end up in an environment where you've rerun it. So interoperability in that sense doesn't really work, and so often, you don't interoperate, and you end up copying and pasting a lot of things, and it takes a lot of extra work to turn some bit of an analysis into a generalizable library, and often these are skills that many scientists don't have, or they don't have the time to bother to turn it into a Python library and put it up on the package manager and so on. Reproducibility and reusability. Notoriously, computational notebooks are not reproducible because of the imperative programming model there, and you can execute cells out of order, all those kinds of things. And then I just talked about some of the reusability issues there as well. And then liveness, right? So you actually kind of just get a snapshot of the notebook as it ran the last time it was run, and when new data or models arise, these things aren't linked in any really direct way, and so you have to rerun everything yourself, and if they're linked using copy and paste, for example, then updates in one place aren't going to propagate to the other place where that same logic might exist. So these criteria by default are not satisfied by notebooks, and I think that causes a lot of problems. So we've been doing a lot of thinking about kind of the future of the scientific workflows. And we have a proposal, and this paper is really more of a proposal and kind of a description of ongoing work and ongoing thinking that we're doing. And so in this paper, we propose this system called Fairground. And what Fairground is it's a computational commons where we imagine thousands of scientific artifacts, to include notebooks and papers and data sets and things like that, are authored, collected, and maintained collaboratively in a form that is executable, interoperable, and that maintains these FAIR criteria and liveness through default usage, through the normal usage of the tool, without having to put in a bunch of extra work. And I think that's really the critical thing that I want to communicate here, is the defaults really matter here. And so let me talk to you a little bit about this idea. And this is really just a start of a conversation. So I'd love to talk to you all about how you would like such a system to work, and what some of the criteria that you would have in the domains that you all work in. So what do I mean by a computational commons? Okay, so I like using this phrase. What do I mean by that? So it comes from the phrase kind of a commons, or in particular, we're inspired by other digital commons. So of course, you're familiar with digital commons like Wikipedia and GitHub. Scientists often develop digital commons to collect scientific data sets and code repositories that are contributed to these commons. And the idea is, you want people to work together to develop these shared digital resources. But what's missing, I think, in a lot of the digital commons that we have today is computation. So even GitHub, and certainly something like Wikipedia, it's really just a place where you put kind of the results of a computation, right? You put in, you paste in a table or a figure. Or with GitHub, you might put in results, or you might put in the source code, but the computation and the configuration of that computation and all of that stuff is somewhere else, right? And I think that's really not the right way to proceed in the future. I think the future digital commons must be a computational engine in some way. It must compute kind of natively, and the computation has to live together with the data and the code. And so here's kind of the provocative thing that we want to think of Fairground as, is we want to formally think of it as a single massive program, a single massive live program. So a program that's being edited and executed continuously, And this editing is happening collaboratively by thousands of contributors. So we imagine thousands of humans of various persuasions, right? Scientists, journalists, scientists with various expertise, not just computer science experts. And then increasingly, I'll just mention, of course, that safely sandboxed AIs are kind of an important part of the vision for the future of computing, and we want them to be participants in this collaboration as well, with, like I said, safe sandboxes to operate within. So how do we build this single massive live program, and you know, what are the research questions there is kind of what we've been thinking about. So last year at PROPL, we introduced some of these ideas, and we discussed the user experience, like what would it feel like as a user to work within such a commons. And we really don't want the user experience of this to feel kind of foreign to scientists. We want it to feel like working in a notebook or working in an authoring environment, editing a wiki, a Wikipedia page, something like that. And I think there's been a lot of interesting ideas. I won't go through all of the ideas that we discussed in the paper last year, but take a look at the PROPL talk that Alexander gave last year for some great demos. But you can see here that there's different users, maybe journalists and scientists. This kind of looks like a paper, except in the sense that kind of Rolly was getting at. We incorporate computation into this directly. So if you click on a histogram here, you can actually see the code that generated it. Maybe you can actually manipulate it in some way. We imagine a system where you integrate both graphical editing and symbolic editing together, and we've done various work in that space. So things like these sliders and bar charts are all part of the code. They're not sitting separately from the code. Okay, so the user experience, I think, is a really important aspect of this. You can't really introduce a new system like this if the user experience is bad, and I think so. UX has to be part of the design from the start. But this PROPL, what I want to discuss are some aspects related to languages and systems, that the underlying systems that would go into building something like Fairground. So the most obvious question, especially in a community like this, is if we want to write a single massive live program that's being collaboratively edited, well, what language is that single massive live program being written in? Great. So, I mean, I think the answer is obvious. Like all great scientific software, it should be written in Fortran. Okay, see you later. Well, I also heard OCaml, and I didn't hear Python, but probably many scientists would say Python, and other scientists would say R, and others would say Julia, and others would say MATLAB. And then there'd be the grumpy one that would say, I write all my code in C, right? So, and then, of course, we would all say OCaml, right? So, I think this is a really important question, and it's one that we have to confront as a community, right? That these languages all exist. They all have large communities with large fan bases in the scientific community, and people aren't really ready to give up on the languages that they work in. And I say this as someone that I design new programming languages. I'm really kind of not excited about existing languages. We really have to confront that problem. And so I think the real answer to this question is yes. Okay, so in other words, I think what we need is an orchestration language that supports this mission of a single massive live program. And one of the central kind of aspects of an orchestration language is that it has foreign function interfaces to various existing languages that people use in the community. And maybe this orchestration language is one in which you can kind of hope people transition to it's maybe more native features in the future, but this FFI problem is one that I want to discuss quite a bit. Okay, so if we're going to design an orchestration language for Fairground, let's talk about its design and its implementation. So what are the design and implementation criteria for Fairground's orchestration language? And so I'm going to talk about kind of three things here. To support interoperability, what we need is a language, like I said, with a robust and customizable foreign function interface, or FFI. And I also think we need to think very seriously, not just about foreign functions, but about foreign data interfaces as well. So I'll talk a little bit about that. And then interoperability, I think it requires some sort of data format for what is the common data format across the system. And I think there's been a lot of work across computer science on data formats. I think as a programming languages community, we should really kind of embrace the essentials of type systems here and use type systems as the core of interoperability. And so I'm going to talk about those things. To support these criteria of reproducibility and liveness, we need to not allow computations to kind of go willy-nilly on the entire world, but we need to instead control dependencies that these computations have, because we're going to be working with code that has maybe even conflicting dependencies, and we need to control side effects. It's really important for reproducibility and for liveness to not just kind of allow the code to have irreversible side effects, on the world. Also, to support liveness, in particular liveness at scale, we need the implementation of this language to scale in various ways. And so if we have a program that's being edited constantly by thousands of people, we can't have any kind of operation that happens in a batch way across the entire program. Think of a program the size of Wikipedia. We can't have every edit to it cause a retype check of the whole thing. And so we need incremental, parallel, distributed, and what I call gap-free, meaning like if there's a bug or there's a missing piece in the program, it can't all shut down. So gap-free, type checking, and program execution, and anything else, program analysis, etc. So I'm going to talk a little bit about all of these things, and I'd love to talk more about all of these things throughout the week. So let me start with the foreign function interface, and in particular, there's kind of an interaction between the FFI and this kind of need to control dependencies and side effects. So the problem is, FFI systems, like even for pure languages like Haskell, often just kind of let you do whatever you want in that foreign code. So they permit kind of uncontrolled code execution, and the stuff that happens in that foreign code can inhibit these criteria that we care about: reproducibility, incrementality, parallelizability, etc. And so what we need to solve as a community, and I don't have a solution to this, but I have maybe kind of the direction we need to go in, is we need a language with an FFI where foreign code must, and truly must, one, execute in some sort of isolated execution environment where the dependencies are managed in some way. And so I think it would be a good thing to explore using a build system designed for reproducible builds, for example, Nix. And I think there's other candidates here as well to consider. And then two, the side effects of this external code need to be controlled in some way. So obviously when you run a simulation, it needs to access hardware, it needs to access file systems sometimes, things like that. But if we can kind of encapsulate that and treat those as kind of internal effects, then what we need to do is ensure that the interoperability with the rest of the commons, all the other codes, or the stuff coming into the simulation and the stuff coming out of the simulation, it's mediated by this pure typed functional interface, and the side effects are kind of managed in some way, so that ideally you have reproducibility. When you run it with the same inputs flowing in from the rest of the commons, it gives you the same output, and so you can manage it as kind of a foreign node in your data flow graph, something like that. And so I'm not really aware of a lot of work on really kind of pure FFI systems, like the systems that really try to manage the foreign code in this way. So I think that's something that would be really interesting for us to work on. And if you're aware of something I'm not aware of, please let me know. Okay, so that's the foreign function interface. I also want to talk about this foreign data interface idea. So the problem is, data in scientific work is often very large, right? It could be petabytes of data out there. It's often stored externally in some way that is very expensive. So it's not realistic to just kind of pull the entire data set into the commons, but rather we need the runtime system of the commons to pull kind of as needed the bits that are needed for the computation that's currently being expressed, or even to push computations to the data sources. So often you have data sources that support queries in some way, or that can run certain computations locally. And so we want to take advantage of that and not have this sort of like world where everything has to be pulled in. And so I think this actually needs to be built in at a pretty deep level in the system, where you have a foreign data interface, kind of like a foreign function interface, where the foreign data is described using the type system, but it's not actually, the values don't exist in the code, but rather are accessed via some sort of customizable access protocol. So how do you access that data? Is it some sort of web query? Is it something else? And then how should the live runtime in particular, if we want this thing to be running and updating live, how should it determine when the data that you're depending on in this foreign source has changed in some way? Can we trust that it's immutable and so we never need to worry about it changing? Or does it update every day from a satellite? Or does it need to be polled every 12 hours or something like that? So I think all of those kinds of configurations should be part of the commons and kind of used by the foreign data interface system. And then, I think there's opportunities to integrate with systems like Spark or other functional data flow engines that have been designed to intelligently query large data sets and even to push computations out to these data sets when appropriate. So Spark has this push down API that's, I think, really interesting to think about here. Okay, so I think there's lots of interesting questions in how do we work with foreign data in a programming language. And then finally, I want to talk a little bit about liveness at scale. And so this problem of having all your tooling really work on arbitrarily large programs. And in particular, your type checker and execution engine needs to be not just incremental to small changes, but constantly updating in response to small changes. Like imagine if Wikipedia were a program, there's little edits to Wikipedia every, millisecond essentially, right? So we need an engine that supports that, and I don't think we have such a thing in computer science today. We also want kind of auto-parallelization. There shouldn't be an inherent order to all the scientific code in the world. That makes no sense, right? We want it to be distributed across all the hardware that we have access to at our institutions and so on. And we want this kind of gap freedom as well. And so there are a number of open problems here. One thing I'll point out is the type checking problem is something that we've, I think, addressed in theory. So if you're interested in how we do incremental and parallel type checking, we have a talk this Thursday at 2:15. So Thomas is going to give this talk on incremental type checking. I think it's really cool work. It won distinguished paper. Hooray. So we're working on scaling this up to full-scale languages, so it's solved in theory at least. But we think the type checking problem is something we have a handle on, although there's probably more open problems here. An open-ish problem, I think, is the execution side of this. So if we're modifying this program constantly, we need to be only re-executing exactly what needs recomputation. So I say it's an open-ish problem because there's relevant prior work. We have some prior work on live programming with holes where we can execute programs as they're being edited and are partially complete. There's been work on incremental and parallel build systems that's relevant here, incremental and parallel spreadsheet execution. There was a number of papers on that problem in the past several decades that I think are relevant here. Auto-incrementalization and parallelization for functional data flow has had a lot of work put into it, but things like Spark. So I think integrating all those ideas and expanding these ideas into just really a general incremental and parallel live execution engine for a general purpose language where we do make the assumption that the program itself, not just the inputs to a fixed function, but the programs itself for changing every few milliseconds, I think, is important. And because some of these recomputations are going to take time, we want to intelligently handle stale prior results. So awaiting upstream recomputations, can we indicate that in some way and still give access to prior versions of the results with some kind of flag on it? So that's all I wanted to talk about there. So those are some of the things that we are thinking about. We're working on some aspect of all these problems in the Hazel project, so we're open to collaboration there. But we think these are also just general problems CS folks should be thinking about in whatever setting they work in. And then I'll close with kind of just a note on AI and how that integrates with these ideas. So I think AI actually creates an opportunity, a unique opportunity for a new computational commons. So if we have such a system, right, if we've solved the PL and systems and HCI problems, I think AI will allow us to rapidly ingest a large amount of existing code and data into this commons kind of semi-automatically, which, the network effects will be maybe lessened in that. Then I also think AI will work better within such a commons. So we had a paper at UPSA last year where we showed that kind of using a semantic context is really helpful. So I'll kind of stop there, or let me just kind of mention. So I think all of these criteria can be addressed in such a system. Findability and accessibility is kind of inherent to putting everything in a commons. You have to think about access control. We talked a lot today about interoperability and reproducibility and liveness. So I think there's really the ingredients for all of these things to be kind of addressed by default in such a system. And so I will stop there.
May I also ask the next speaker comes in?
Thanks a lot, Cyrus. That was super nicely articulated vision. So I had a question about the kind of liveness at scale and interoperability. Yeah. So if you've got heterogeneous environment, different languages potentially, you can imagine the same kind of problem coming up with data provenance as well, where you've got kind of different systems that need to talk to each other. How are you imagining the kind of what you call the foreign data interface would need to be like in order to support liveness at scale? Do you need to kind of potentially maintaining data information about what's changed. So, for example, if I've got a large data structure that's changing, I don't want to recompute, because there's a whole bunch of downstream computation that depends on the whole matrix or whatever it may be.
Mm-hmm.
I may know that just one cell has changed,
Yeah.
and I might just want to sort of publish that information as part of the revision to the data. So, do you think the foreign data interface would need to support that notion?
Yeah, I think the foreign data interface should have some pretty kind of fine-grained way to express change. If you don't have some, the right information to express the fine-grained change, then you can do some coarse-grained kind of analysis. But ideally, maybe some of your work on kind of provenance is relevant here. If we can really kind of capture what exactly changed, we can, and then, forward that through all the dependency analyses. I think that would be really ideal.